Okay, so now we're going to apply the idea of work to this problem, 9.18. Okay, so we've got these three forces that are acting on this grand piano, and we are lowering this piano 5 meters from a second-story window. Okay. Because we are lowering this piano, we are going to make the assumption that we are moving it with the constant velocity, although that's not going to really come up right now. But we're going to, just so that we can understand the problem, we're going to assume that this piano is moving slowly at a constant velocity. Okay, so we're going to start out with work. We're going to find the work done from each of these forces individually. And we're going to use this expression, F dot delta R. Okay, we don't need to integrate anything in this problem because all of our forces are constant forces. None of them are functions, so we can be thankful for that for now. All right, so let's find the work done by tension 1. Okay, let's write our expression. And in this case, the force is, actually, we can just say tension 1. Okay, so tension 1 is equal to 1,830 newtons. And here, because we're lowering this downward, our delta Y is downward, okay? So, actually, you know what? I want to back up and I want to do a diagram here. So let's do a diagram of that first force. Okay. So the diagrams this time are going to be a little bit different. So the diagrams are going to show, it's going to show the force and your delta R and the angle. Okay, so it's going to be like this. So we're going to draw tension 1. So tension 1 is kind of up like that. And we're going to draw tails to tails. Now the displacement. This is not a force diagram. Okay, this is not a regular force or a free body diagram. Okay, this is a special kind of diagram that we're doing when we are doing work. Okay, so we've got our two vectors. Okay, so we have a force vector, we have our displacement vector, and we want to know the angle between them because that is our angle phi. Okay, so we have our delta y. Our delta y is 5 meters. Notice that this is not negative. Okay, so there's no negative in here. And the reason is, yes, it's downward and it is negative. However, all of the direction and positive and negative information is going to come out of this dot product that we're going to use with our vectors and the angle between the vectors. So we are not going to assign this vector to be negative. We're going to let it come out in the wash. So now we go over here to our work. And now this is going to be, I'm going to make this tension 1, dot it into delta y. Okay, so now I'm going to write that out. I know that anything dotted into something else, it's going to be magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between those two vectors. Okay, and this, I'm going to call this phi 1. Every vector, or I should say every force, is going to have its own unique value for phi. You can see already in the diagram that the angles are different for each force. Okay, so now, remember we're looking at the angle between the vector tension 1 and delta y. So that's going to be 150 degrees. Yeah, so it's 60 degrees plus 90 degrees. Okay, so now let's plug and chug and see what we get. Okay, so the magnitude of tension 1, okay, and then the magnitude of the displacement times the cosine of 150 degrees. Okay, let's see what that gives us. Okay, so that gives us, let's just keep 3 sig figs. So we'll go 7920. I'm just going to round that off. Okay, and now let's look at the units. The units are newtons times meters, and newtons times meters are joules. Okay, so let me just show you that over here. So Newton times meters, that's going to be kilogram meters per second squared times another meter. And that gives us kilogram meters squared per second squared, which is defined to be the joule. So that's the unit that we're going to be using for all energy measurements and units. Okay, so that means that we had negative work done from tension 1. So let's just ask ourselves, what does that mean to have negative work? So remember, negative work means that energy was removed from the system from that force. So imagine if you did not have any tension whatsoever. Let's just say instead of lowering the piano out the window, you just dropped it out. So if you just dropped it out the window, then there's going to be a lot of energy that you notice is in that piano by the time it crashes and smashes all over the place. You want to remove some of that energy so that you don't get the crashing and the smashing at the end. So that's what tension 1 is doing. It's removing some of the energy from the system. That's why it's a negative amount of work that it does. All right, let's do the next one. Let's do tension 2. Okay, so tension 2. Let's make the diagram for tension 2 and the displacement. Okay, so tension 2 is at a 45-degree angle. Okay, so tension 2. And it's always with the displacement delta y. And now phi 2 is in here. And that's going to be 45 degrees plus 90 degrees. All right. So now let's get our equation. Okay. And we know that tension 2 is 1295 newtons. Delta y is still 5 meters. And now phi 2 is 135 degrees. Okay, so this is going to be T2 dotted into delta y. Okay, so that's going to be T2 times delta y times cosine of phi 2. Which we can now plug in and see what we get. All right, let's see what that gives us. Okay, so another negative value, negative 45. We'll just call it 4580. We'll keep it to 3 sig figs again. Okay, and joules is the unit. Again, we're looking for this other tension force to remove some energy so that the piano doesn't smash. All right, so now let's do the last force, and that's going to be the weight. Okay, or F sub G. All right, so let's get our diagram. Okay, so here's the weight, that's the force. Here's the delta y. What's the angle between those two vectors? Well, this time we've got F sub G, that's equal to 2,500 newtons. And we know that delta y is still 5 meters. But phi 3 is 0. Okay, so let's see how much work is done this time. Okay, so this is going to be F sub g dotted into delta y. Okay, so that's going to be F sub g times delta y times the cosine of the angle between them, which is 0. Okay, so the cosine of 0 is 1, so this all goes to 1, meaning that the work done is going to be F sub g times delta y. All right, so 2,500 newtons times 5 meters. Okay, that gives us 12,500 joules, positive. Okay, so gravity is doing positive work. Okay, so if you think about it, remember positive work means that the energy of the system increases. So if gravity were the only force acting, if we had this piano in free fall, then gravity would be doing the work to add energy to the system, and you would certainly see evidence of that energy whenever it hit the ground and smashed everywhere. Okay, so even though this question, this problem didn't ask us to find the net amount of work or the total amount of work, I'm going to add that as a question, so we're going to do that. So with all three of these forces acting, each one can be contributing their own amount of work, whether it's positive, negative, or 0. But when we add them all together, that's when we get the total. So let's see what we get here. Okay, so let's find work net or work total, however you want to call that. Okay, so work total is going to be the work done by tension 1 plus the work done by tension 2 plus the work done by the force of gravity. Let's see what we get. Okay, so the work done by tension 1 was negative 7920 joules. Okay, then the next one was negative 4580 joules. And then 12,500 joules. When you add those all up, guess what you get? You get a 0. Boing. Okay, so what does that 0 mean? Well, remember we had, in this situation, we had constant velocity. We were lowering that piano down slowly. Well, whatever the speed is, it doesn't matter, but it's a constant velocity. So constant velocity, kinetic energy, remember, is 1/2 mv squared. So if you have a constant velocity, that means you have a constant kinetic energy, right? So if you have a constant kinetic energy, then that means if this is 0, no change in your kinetic energy, this has to be 0 also. And that is what we got.